another couple of minutes and we start at around 1:10 or something. I think I remember last time we discussed up to this point. No? Am I correct? Oh, we discussed this also. 2.4. Did we discuss this 2.4 also? Definition 2.4, bounded above, bounded below, and bounded sequence. Can one of you respond to me, please?
Recording in progress.
Can one of you respond to me, please?
Yes, sir.
Okay, 2.4 also we already discussed. Okay, anyway, I repeat this 2.4 again because we want to do this exercise. Right, okay, fine. So 2.4, it says about the bounded above, bounded below, and bounded sequence. Okay, so these are the definition for bounded above sequence, bounded below sequence, and bounded sequence. Okay, there are three terms here. One is the bounded above, the other one is the bounded below, and the next one is bounded sequence. Okay, so the definition is very simple. You can read it and understand. A sequence An is said to be bounded above if there exists a real number n such that An is less than n, less than or equal to n for all n belongs to n. That means that if you have the sequence A1, A2, and all these sequence, all the values of the sequence are less than or equal to a real number n. If you have such a real number, then we say that the sequence An is bounded above. Bounded above means it is bounded by a larger number. It is bounded by a larger number. So all the terms of the sequence are less than or equal to that particular number. But similarly, we say that a sequence is bounded below. A sequence is bounded below if there exists a real number m dash such that An is greater than or equal to m dash for all n. That means that this is your sequence A1, this is your sequence A2, and all the terms of this sequence are greater than or equal to a number capital M dash. Okay, so in that case, we say that this sequence is bounded below. In that case, we say that this sequence is bounded below. Okay, so all these terms are greater than this particular number M dash. Okay, so about M dash is it's a real number. It can be a negative or positive number, no problem. Here also it can be a negative or positive number, no problem. Okay, but it's a real number. Then the third definition, a sequence is said to be bounded below. Sorry, a sequence which is bounded above and bounded below is said to be bounded sequence. Okay, that means that if a sequence is bounded above and bounded below, then we say such sequence as bounded sequence. Say for an example, A1, A2, these are comma, okay, in between comma, and this is bounded above by a number capital M. Meantime, it is bounded below by capital M dash. That means all the terms of this sequence are between two. All the terms of the sequence are between two real numbers. Then this sequence An is said to be bounded. So already we have studied bounded above and thing. So they're similar to that one. Okay, so this is bounded. All right. So we have exercise here. It says that exercise here show that the sequence, so that a sequence A is bounded if and only if there exists capital M greater than 0 such that mod of An less than or equal to n for all n. Okay, so this is another definition. You can think like a definition or think like a theorem or something. but here in this exercise, okay. So if you have a positive real number, if you have a positive real number, positive here, look at here, m is a positive real number, okay, real number such that mod of n is less than or equal to that particular m, okay, then for all n greater than 0, for all n belongs to m, then we say that the sequence is bounded. Okay, so proof is given here. So proof is given here. Okay, let me use whiteboard to explain the proof. So here, so we want to prove that the sequence an is bounded okay. The sequence is bounded if and only there exists a capital M, greater than 0, that is a positive real number, such that mod of an is less than that particular m for all n belongs to set of natural numbers. So this is the theorem. It's a theorem or it's an exercise or whatever it is. Okay. So we want to prove this one. So prove so we are going to assume first one, we are going to assume this condition. We are going to have this one. Okay, we are going to have this one. So we are going to take this as, we are going to take this one and we are going to suppose this and we are going to prove that the sequence is bounded. Okay, suppose. So you can later read the proof in your note. The same thing is there. Let me explain here. Suppose there exists capital M greater than 0 such that mod of an is less than for all n belongs to it. Now we are going to prove that an is bounded. Now from this one, what you can say actually, say for an example, if you have something like this, mod of x is less than r. Okay. This is a kind of side note, so it's actually just to explain. If mod of x is less than r, then of course you can write it as minus r less than x less than r. Okay, you can write this, isn't it? So similarly, using this idea, you can write here. You can write here. An is capital M greater than. Okay. So if you want, even you can write these as minus m less than or equal an m for all n belongs to n. E also for all n belongs to. Then from this one, you take, because from this one, if you have something like this, okay, so another side notes. If you have an inequality like this, say for example x is less than 5, then it is nothing wrong writing x is less than or equal to 5. Okay, because less than or equal to O, no, less than O equal. We are not saying that less than and equal. Okay, so if you have something, you can without any problem you can write this because this is O. If x is less than 5, it is nothing wrong writing x is less than or equal to 5. Okay. Similarly, if a number say y is greater than 3, it is nothing wrong writing y is greater than or equal to 3. So that is how I have written here. Now, if you look at this part of this inequality, if you look at this part of this inequality, it says that an is less than or equal to. So there exists m, there exists n, there exists m, such that an is less than or equal. So if you take this part of inequality, it is bounded above, isn't it? If you look at this part of the inequality, you can say that it is bounded above. And if you look at this part of the inequality, and this, including this one, you can say that because for all n, an is greater than or equal to a real number. Okay, so that is the definition for bounded above and bounded below. Here, it doesn't need to be negative or anything. Okay, if you look at the definition, here, the bounded above, if there exists a real number m, if there exists a real number m dash, isn't it? Therefore, we are not worried about whether m is a positive number or negative number. Okay. So in that way, you can say that you have a real number such that an is greater than or equal to a particular real number m. Okay. So you can think like this is where m dash. This is where m dash. So proper thing is there. I'm just explaining the proof. Okay. So this blue color part actually telling that it is bounded here. It is an is sequence an is bounded below. Therefore, from these two parts, you can say that. Therefore, we can say that an is bounded. So from these two results, you can say that an is bounded because one side it is bounded below, the other side it is bounded above. Therefore, you can say that the sequence an is bounded. Okay, so that concludes the first part of the proof. That concludes first part of the proof. That is, if there exists, we are assuming that there exists a positive real number m such that mod of a less than or equal to n. Why we are saying positive m? Because it's a real number. No? It's a mod of a n. No? So mod of a n always will be greater than 0. Therefore, that is why we are saying that this capital M is a positive number. Otherwise you can't have something because mod of a n always should be a positive. Mod of a n always will be a positive. Okay, if it is less than some number, definitely this m should be a positive number. Okay, so that is the first part of the proof. Now the second part is we are assuming, suppose we are saying that mod of okay, we are going to say that the second part is what? Suppose we are going to say that the sequence an is bounded. We are supposing that the sequence AN is bounded. Now we want to show there exists a M, capital M, positive number such that. So now we want to show what? We want to show this part. There exists a positive real number M greater than 0 such that mod of AN less than M for all N belongs to M. Okay, so that is what we want to show. Right. Now we have supposed that AN is bounded. AN is bounded that, then we can say that there exists K, this is simple K, and this is capital K. Okay. So try to understand the difference. This is simple K and this is capital K. So there exists simple K comma capital K belongs to set of real number such that AN is less than or equal to capital K greater than or equal to simple K. Why we can write this one? Because we have supposed that AN is a bounded sequence. Therefore, bounded means there are two parts, above and below. Isn't it? So above and below. So you can say, so since AN is bounded, there should be two numbers. One is capital K and the other one is simple K, such that AN is between the two numbers. Like earlier one. Here I said, look at here. Here we are saying that the sequence is bounded, then there will be two numbers, M dash and capital M. Here, my capital M, my capital K is this one. This is my simple K. That's all. Now, from this one, okay, so this is capital K and this is simple K. Now, I'm saying, I'm defining my capital M as, so we are saying let capital M equal to maximum of mod of simple K, comma, mod of capital K. So let M equal to maximum of mod of capital K, mod of these two. So maximum of these two. If then from this inequality, you can write AN will be always less than or equal to this capital K, okay, less than capital M, greater than or equal to simple K, greater than minus capital M. This is okay, so I am defining, or I am taking capital M as this way. I am taking capital M as this way. Okay, so in that case, I am writing this way. For an example, say for an example, look at here. The AN is between 10. This is example. Just don't write this one. You don't need to. This is not a part of proof. Just I am writing explain. And say minus 5. Okay. Then what you can say? So this is your simple K. This is your capital. Okay. So then you are taking your capital M as maximum of what? Mod of minus 5, comma, mod of 10. Then mod of minus 5 is 5. So this is nothing but maximum of 5, because mod of minus 5 is 5 and mod of 10 is 10. Yeah, 10. So the maximum of 5 comma 10 is actually 10, isn't it? Therefore, this one you can always write it as minus 5 less than or equal to an less than or equal to 10 less than or equal to, or you can simply say less than or less than or equal to 10 greater than or equal to. Okay, that is true, no? That is true. So this is your M. Okay, so if you have a inequality like this, then by defining capital M as maximum of mod of simple k and mod of k, you can always write this inequality. You can always write this inequality. Okay? So if you set your M as maximum of mod of simple k, so simple k and this capital K, then always you can write this. Okay, so this is just for your understanding. This is not part of the proof. So this is just for your understanding. Okay. So now, so there exists. So here you can write this. There exists k comma k1 case such that k is less than or equal to a, k is less than or equal to capital K for all n belongs to n. Okay. So that is important. Then here the same continues here for all n belongs to n. Therefore, from this one, if you just leave this one, so from this one you understand that minus m less than minus m is less than an is less than capital M for all n belongs to n. So this is nothing but mod of an less than capital. Okay, so we can conclude that there exists capital M greater than 0 such that mod of an less than capital M for all n belongs to n. So that concludes the proof. That is what we want to prove. Now here, how can I say that this is a positive number? How can I say that this is a positive number? Because if you look at here, I'm taking capital M. I'm defining my capital M as maximum of mod of capital K, mod of simple K, comma mod of capital K. So whatever the value of K, here I'm not restricting K, but here when I'm defining my M, I'm taking the mod of these two numbers. Therefore, definitely this is a positive number. Definitely this is a positive number. Okay, therefore I can firmly tell that there exists capital M greater than 0 such that mod of an less than capital M for all n. Okay, so that concludes. Okay, so there are two parts actually. You have to understand that. One is at the beginning we are assuming that an is bounded. If and only this is a theorem for exercise, whatever it is, you can take it. Now, this is what we want to prove. In the first part of the proof, we are assuming this one. There exists a positive real number M such that mod of an is less than capital M for all n belongs to n. So we are taking this condition and we are using this inequality we studied in real analysis. If you have some inequality in this form, mod of x less than r, always you can write x is between plus r and minus r. Then using that one, if you get rid of mod, then you can write it as minus m less than an less than capital M. If you want, you can put equal sign because it's O. Therefore, if you take this part of this proof, then that gives you it is bounded above. And if you take this part of this inequality, it gives you bounded below. So combining these two results, you can say that an is bounded. Now we want to prove we are going to assume an is bounded, and we are going to prove this part. Okay, so I am supposing that an is bounded. That means that bounded above and bounded below. Then since it's bounded, I can say that there are two real numbers. Two real numbers, simple K and capital K, such that an is between that two real numbers. Now, if I choose capital M as maximum of these two numbers, then always I can be able to write an is between K and minus K, less than capital M, greater than minus capital M, as I explained. Okay? As I explained. Therefore, then now I don't want this K anymore. So I'm just dropping this K, and now I'm having the inequality that an is between capital M and minus capital M. Therefore, now if I use this definition again, if I use this inequality result again, okay, inequality result again, then I can say that, so from this one I can say that mod of an is less than n. So I can say that there exists m greater than 0 such that mod of an is n. Therefore, that concludes the proof. We understand? We understand, students? Hello, do you understand this?
Yes, sir.
Okay, fine. So that's all about this one. Now we are moving to another important theorem, that is theorem 2.2, okay, which is very, very important. So it says that every convergent sequence is bounded, but it says that the converse is not true. So if you have a convergent sequence, you know the meaning of convergent sequence. When we say a sequence is convergent, okay, so we have a definition for that. So if you have a convergent sequence, this says that the sequence will be definitely bounded. Bounded means bounded above and bounded below. Okay, but the converse is not true. That means that if a sequence is bounded, that need not to be converged. Okay, so here to show this one, it is enough to give a counter example. Okay, but here the first part of this theorem you have to prove. This one you have to prove. That means that every convergent sequence is bounded. But this is counter example. So we'll look at this proof now and we'll try to understand. Okay. So let me again use my whiteboard to explain this now. So theorem 2.2, it says that every convergent sequence is bounded. Convergent, I write it in short, implies as an is bounded. Okay, but the converse does not hold. That means that an bounded then we cannot conclude that it is convergent. Okay, so this is okay. Okay, but bounded does not imply that an is convergent. That's what we are going to look at now. Okay, right. Now, right. So I'm going to prove this one. For this part, actually, we are going to give a counter example. For this part, we are going to give a counter example. This part we are going to prove an convergent. So proof. So we are going to suppose this one. Suppose the sequence an is convergent. Suppose AN is convergent. AN is convergent. Suppose AN is convergent. Now, what can you say if a sequence convergent? Suppose AN is converge, so we can say that suppose AN is converge. So we are going to say AN is convergent. Suppose AN is convergent. And limit AN n tends to infinity equal to A. Okay, so that is what I'm going to assume. This one I'm going to assume. So I'm assuming that sequence is convergent and its limit point is A. So now if a sequence converges, what can you say? Say for an example, limit A, then what can you say? Can anyone tell me? What is the definition? If a limit A tends to infinity is A, what can you say? Can anyone tell me, please? So you can say that for all epsilon greater than 0, there exists n belongs to set of natural number such that mod of an minus a less than epsilon for all n greater than or equal to this particular n. Okay, so that is the definition. This is like a side notes. Okay, so if limit n tends to infinity a, so you can say that if and only for all epsilon greater than 0, there exists n belongs to n such that this one. Okay. So here I am supposing the same. Suppose the sequence an is convergent and limit point is a. Now here if you look at this one, this is true for all epsilon, isn't it? This is true for all epsilon. So in this case, I can say that so this implies mod of an minus a. So you can say like this, no? You can say that there exists n belongs to n set of natural number, okay, such that there exists n belongs to n such that mod of an minus a less than 1 for all n greater than or equal to capital N. How can I say? The same thing I have written, but instead of epsilon, I have put 1 here. Why? Because this is, I can write it for particular epsilon also. Isn't it? I can write this for a particular epsilon also. Since limit n tends to infinity equal a, if and only if for all epsilon greater than 0 there exists n belongs to n such that an minus a is less than epsilon for all n greater than or equal to n. No. Therefore, since this is true for any epsilon, in this particular case, I am considering my epsilon as 1. Okay, I am choosing my epsilon as 1. So if you want, you can write here epsilon. I am choosing my epsilon as 1 because for all epsilon it is true. So choose epsilon equal 1. That's all. Okay, that's all. Then what you can say that? Then you can say that. So this implies this. Let me write this in a different way. Okay. Now I'm going to consider mod of an, which is equal to, I can write it as an. Okay, I can write this as yeah, an. So I can write this as, see whether I'm writing is correct or not. A plus so actually I'm writing my an as a plus an minus a. So that 2a can cancel, isn't it? So this is using, this is less than or equal to, okay, this is less than or equal to, using the triangular inequality, always you can write this as mod of a plus mod of an minus a, mod of an minus a. But according to this one, mod of an minus a is less than 1. No? Therefore, you can write this as, this is less than mod of a plus 1. Okay? Mod of a plus 1 when for all n greater than or equal to that particular n. Okay, so this is true for all n greater than or equal to particular n. Okay, now what I can say? Now if I as maximum of, okay, so you see, look at this one, look at this carefully, I'm explaining it again. So here we have proved that there exists, because limit n tends to infinity a, okay, then we can say that there exists n belongs to n such that mod of a minus a is less than 1, because I am choosing my epsilon as 1 for all n greater than n, for all n greater than n. Okay, now I am considering mod of an, but I am writing mod of an in this form, mod of a plus an minus a. Then using the triangular inequality, I can write these as mod of a plus, this is less than or equal to mod of a plus mod of a minus a. But from this one, I can say that mod of a minus a is less than 1 for all n greater than n. So this is true for all n greater than n. Therefore, I am combining that one, and for this one, I am putting less than or equal 1. So this is true when n greater than or equal to n, for all n greater than or equal to n. So that condition is important, because this inequality is true only for n greater than or equal to n. So I am here writing this way. Now this is true for n greater than or equal to n. Okay, so we don't know anything about other terms of this sequence. So I am taking capital M as maximum of A1, A2, dot. The last term I'm considering an minus 1, comma 1 plus mod of a, comma mod of a plus 1. Okay, so here this inequality true for all n greater than 1. Then I am taking the maximum of this part. Say, look at here, I'm explaining this. This is not part of proof. This is not part of proof. I'm explaining here. Look at here. Now we have this sequence A1, A2, dot, A capital N minus 1, comma A capital N, Okay. Now we know that this whole part, okay, this is less than or equal to mod of A plus 1. Mod of A plus 1. Now here mod of A1, mod of A2. So if I pick maximum of this one, say for an example, okay, so maximum of this up to this point, okay, say A1, A2, an minus 1. Okay. So now if I take the maximum of these numbers, this number and this number, okay, if I take the maximum of this number and this number, definitely what I can say, mod of an will be less than that particular m, isn't it? If I pick the maximum of this number and this number, because for all these terms they are less than or equal to this one, so maximum is this one. For these numbers I don't know the maximum, so if I take my capital M as maximum of this number and this number, then I can say that my an will be less than m for all n belongs to m. Here actually this is true only for n greater than n. Therefore, if I take my m as this way, then I can say that. So this is not part of proof. This is just I'm explaining here. Okay, so up to this point, you can just for your understanding. Okay. So from this one, I can say that mod of an is less than m now for all n belongs to m. So from the previous exercise, what do you know about this one? If mod of n is less than m, and also you know that m is a positive number because capital A is positive, mod of capital A is positive, plus 1 is positive, mod of all these numbers are positive. Therefore, obviously this is a positive number, isn't it? Therefore, what you can say, we have mod of an, this is not minus, huh? So mod of an less than or equal to 4 whole n. So we can say that there exists capital M positive number such that mod of an is less than m for all n belongs to m. So this says that the sequence an is bounded. So that's the proof. That is the end of the proof. The sequence an is bounded. Okay. So sequence is bounded. So now we have to do the first part of this. We understand this one. This is done now. We understand. We understand, students? Hello. We understand. Right. Only if you are responding. Only if you are responding. What about others? You can use the chat box, meeting chat, to ask any questions if you want, or just to respond whether you understood or you want me to explain this again or whatever it is. Okay. Right. Right. Now, the second part, which says that the converse is not true. Second part of this book says that the converse is not true. That means that the sequence may be a bounded one, but it doesn't need to be a convergent one. It doesn't need to be a convergent one. Say, for this case, we have to give a counter example. Okay. Sequence may be bounded, It doesn't need to imply AN is convergent. So example, consider the sequence AN with the term AN equal minus 1 to the power n. Minus 1 to the power n. Obviously, we know that mod of AN, that is equal to mod of minus 1 to the power n, okay, less than or equal to 1, isn't it? Less than or equal to 1, because when it is positive number, it is plus 1, and when it is negative number, it is minus 1. So AN is always between what? Less than or equal to plus 1 and greater than or equal to minus 1, isn't it? Hence it is bounded. Hence AN is bounded. Hence AN is bounded. But we have already seen that. The sequence, we have already seen that the sequence minus 1 to the power n does not converge. But the sequence minus 1 to the power n does not converge, because it oscillates between plus 1 and minus 1. Okay, does not converge. Okay, so this is one of the counter example. There are more examples. You can pick. You can give any example you want, but this is one of the simplest example, which shows that the sequence may be bounded, but it doesn't need to be converged. It doesn't need to be converged. Okay, it doesn't need to be converged. So this is right. So now we understand. Do you understand this, friends? Please tell me.
Yes, sir.
Okay. 146. Whether you understand. And 46. Do you understand? 157. Do you understand?
Yes, sir.
134. Are you there? Hundred and 37.
Yes, sir.
95. Do you understand?
Yes, sir.
76. Do you understand? 62. Do you understand? 39. Are you there?
Yes, sir.
31. 15. Do you understand?
Yes, sir.
42. Okay, right. Anyway, now we are saying that if a sequence is bounded, then it doesn't need to be convergent. It doesn't need to be convergent. Some of the bounded sequence may be convergent. Okay, some of the bounded sequence may be convergent, but some of the bounded sequence may not be convergent. But every convergent sequence is bounded. So you have to understand, that is the key point that you have to take it from here. So every convergent sequence is bounded. So we have the theorem that every convergent sequence is bounded. So we have every convergence sequence. Every convergence sequence implies as bounded. So if I take this one, so if I take this is my P, statement P, proposition P, and if I take this as my proposition Q, then the P implies Q. The proposition P implies the proposition Q. Now, if I take negation of this one, the negation of Q implies as negation of P. So what is the meaning of this one? We know that in mathematical logic, you might have studied that P implies Q is actually equivalent to what? Negation Q implies as negation P, isn't it? So these two are equal. Therefore, if P implies Q, you can say that negation P implies as negation P. Therefore, from this one, you can conclude that this is true. Already we have proved this is true. But these two are equal. Therefore, from this statement, you can write that. From this statement, you can write that if a sequence, negation Q mean what? Not bounded. So you can say that not bounded implies as not convergent. So that is also true, because from this mathematical logic, so if you show one particular sequence is not bounded, then it implies that it is not convergent. So if you want to show a particular sequence is not convergent, then if you show it is not bounded, then it is sufficient. Or it is indirectly saying that the sequence is not. Okay, so this negation of this mathematical logic, this mathematical implication is applied to show the particular sequence is not convergent. Okay, so if you want to show in some cases a sequence is not convergent, if you say not bounded, the sequence is not bounded, then that is not convergent. You understand? So here, if you look at one example in your handout, we are given a sequence. So that is what it says. The above theorem can be used to show a certain sequence is not convergent, as in the following example. Why? Because we know that if we take this as P implies Q, then we know that obviously this is equivalent to negation P implies as negation P. So if a sequence is not bounded, that will imply that it is not convergent. It is not convergent. Therefore, it says that the above theorem can be used to show that a certain sequence is not convergent. How? If we show that the particular sequence is not bounded, then that will automatically showing that the sequence is not convergent. Okay? Do you understand? Do you understand, students? Hello, do you understand? Please text me. Please respond to me. Respond to my questions. Otherwise, how can I know whether you understand or not? Can one of you answer me, please?
Yes, sir.
What's your name?
Halim, sir.
Ali. Okay. What's your registration number?
140.
14. Right, okay, fine. Now we are going to show this particular sequence. The sequence given by an equal 1 plus 1 half plus this one is not converged. So we want to show, so exercise, for example, we want to show sequence an given by 1 plus 1 over 2 plus 1 over 3 plus dot 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 1 over n. Carefully look at it. This is one term of the sequence. Okay, sequence is not 1 over n. Okay, say for an example, if you take the first term, a1 is actually only one term, 1. Okay, a2 is having 2 terms, that is 1 plus half. Okay, a3 means 1 plus half plus 1 over 3. So in that manner, the sequence goes. Okay, so this is the sequence. Now we want to prove that this sequence is not converged. This sequence is not converged. So we are not going to directly prove that this sequence is converged. What we are going to do is, we are going to use the contraposition of the previous theorem. Contraposition means what? What is contraposition? If P implies Q, then negation Q implies as negation Q. So this is called contraposition. So we are going to use the contraposition of the previous theorem to prove that this is not a convergent sequence. So what we are going to do is, we are going to show the sequence is not bounded. Sequence is not bounded. This is convergent. This is bounded. Okay. So if we say not bounded, then that will automatically imply that the sequence is not convergent. Therefore, what we are going to show is, we are going to use that. Okay. For that one, here I am considering one term. I am going to consider a to the power a, the 2nth term. 2 to the power nth term. I am considering this one for some purpose. Okay. Because I am going to use some mathematical techniques. That is why I am considering this term. This is also one of the term in that sequence. Okay. This is also one of the term in that sequence. Here we have n natural number. First number is 1, 2, goes n plus 1. And that way, there will be one term where the value of n will be 2 to the power n. I am considering that particular term. I am considering that particular term for some purpose, because I need some more terms in order to use some mathematical techniques. Okay, so if I write the a2n term, then that will be 1 plus half plus dot dot dot. So if it is an, it will go up to 1 over n, isn't it? So here I am considering a to the power a 2nth term. Therefore, that will go up to 1 over 2 to the power n. 1 over 2 to the power n. Okay, 1 over 2 to the power n. Now what I am going to do is I am going to group these terms. Okay, so like this. Look at here. So here I am considering this term, a to the power 2n term. Then this term I can write it as 1 plus half plus 1 over 3 up to this one, up to 1 over 2n. There will be how many terms here? If you take an, there are n terms. There are n terms, isn't it? There are n terms. So similarly here you have 2 to the power n terms. You have 2 to the power n terms. Then what I am doing is, okay, what I am doing is I am grouping the terms. First term I am writing as it is. Second term I am writing as it is. I am combining third and fourth term. Then fifth, sixth, seventh, eighth term together. Likewise, I am combining. Likewise, I am combining. Here 2 terms, here 4 terms, next 8 terms, and in that way I am grouping this one. Then obviously, if you look at this one, this is 1 over 3 plus 1 over 4. If you look at 1 over 3 plus 1 over 4, okay, 1 over 3 plus 1 over 4, this is always less than half, isn't it? This is always less than half, because if you take 12 as the LCM, least common multiple, then this is 4 plus 3, no? 4 plus 3, okay, 4 plus 3. So 4 plus 3. So 4 plus 3, then what? So this is greater than half. No? So this is greater than half. So this is greater than half. So each of these terms, if you look at each of this term, if you look at each of this term, okay, if you look at each of this term, this is greater than half. This is greater than half. This is greater than half. So in that way, if you look at here, there will be, including this one, there will be n groups. Okay, this is 1, this is 2, this is 3. Likewise, there will be n. Okay, so each of this term is half, less than half. Each of this term is less than half, and there are n groups. There are n groups. Therefore, you can write this whole thing as greater than or equal to n by 2, because each of this one is greater than half, and there are n groups. Therefore, you can write these as greater than equal to half. Already we have one here. Therefore, I am writing in this way. Therefore, using the inequality, the truth of some inequality, the results of some inequality, always you can write this. Always you can write this. Therefore, now if you look at this one, this a to n is always greater than or equal to 1 plus n by 2. Okay, 1 plus n by 2. Okay, this is always greater, but when n tends to infinity, this automatically goes to infinity, isn't it? When n tends to infinity, this automatically goes to infinity. But a 2 to the power n is less than this one. Sorry, a 2 to the power n is greater than this one. Okay, so even smaller of this goes to infinity. Therefore, what will happen? A 2 to the power n, it goes to infinity as n tends to infinity. Therefore, this is not bounded. Therefore, the sequence A is not bounded. Sequence A is not bounded. Therefore, since it is not bounded, it is not convergent. That means that it diverges. So this is how we are trying to prove this one. This is how we are trying to prove this one. Okay. So nothing else. Why we are considering a to the power 2n? So in order to use some mathematical techniques, we are considering the term a 2 to the power n, nothing else. There is no any other reason considering the term a 2 to the power n, because when you consider n, then it is very difficult for you to show this way. That is why we are considering a 2 to the power n term, and we are grouping those terms in this one, and each of these group is always greater than or equal to half, and there will be n groups. Therefore, you can always write this is greater than or equal to 1 plus n by 2. But now What is the conclusion? 1 plus n by 2 is always less than or equal to a 2 to the power n, isn't it? But automatically, already we know that this goes to infinity. As n tends to infinity, this is not a bounded one. This sequence is not a bounded one. The lower bound, the least one is not bounded. So this is not bounded, but this sequence is even greater than that one. Therefore, definitely this is also not bounded. Okay, since n is an arbitrary one, you can now say that n is not bounded because this is one of the term in that sequence. Therefore, now we can say that n is not bounded sequence. So A is not bounded sequence. So how we can say this diverges? Because we are using the contrapositive of this theorem. That is, if it is not bounded, then it is not converged. Therefore, by showing that the sequence is not bounded, we are trying to say that the sequence diverges. You understand? You understand, students? Hello, do you understand? Okay. Now, the last theorem we don't need proof for this one. This says that suppose A tends to A and B tends to B. So the sequence A and the limit point of sequence A is A, and the limit point of sequence B is B as it tends to B. Then we have the following. That means that the sequence A and B, the sequence A and B, that the sequence formed by multiplying these two sequences goes to AB. Okay, so that is one thing. Another one, if Bn is not equal to 0 for all n. Why we are saying that Bn is not equal to 0? Because we are going to have a sequence in this form, An over Bn form. An over Bn form. Therefore, Bn should not be equal to 0 for any n. Otherwise there will be some kind of infinity term in the sequence that is not accepted. And B is also not equal to 0. That means that the sequence Bn does not converge to 0. In that case, the sequence formed by dividing the sequence An by Bn, okay, will converge to the limit point A over B. Okay, so this is what actually mentioned in this theorem. Sometimes this is useful when you have to find the limit point of, when you have to find limit points of some complicated sequences. If you know the sequence, the limit point of A and B, then Bn, then you can easily find the multiplication of those two. Or similarly, you can find the division of those two in this case. Okay, so that's end of this handout number 4, and hopefully you would have done this question. And if you have a doubt or if you have any, if you want me to show this, if you want me to do this and show the answer, then we'll do the during the tutorial discussion when faculty reopens physically. Okay. So I want to finally, before your final exam, I want to do a tutorial questions, and I want to tell you something about the final exam paper. I want to discuss the structure of the final exam paper. So during that session, I will discuss some important problems. Okay, important problems. Okay, but okay. Anyway, now, so please, 77. Don't you understand this one? 77. Don't you understand this one? Which one you understand? Which one you didn't understand? 77. 77. Can you tell me which you didn't understand? So I can explain. No problem. I can explain it again. '77. Can you tell me which you didn't understand? Example, last part. Okay. Last part you didn't understand. Okay, let me use here. Okay. Now we want to show that this sequence given by this form. Okay, here this is actually the general term of the sequence. Okay, this is actually general term of the sequence. Okay, so if you take your sequence, the first term of the sequence A1 is equal to actually 1. Okay, A2 is actually equal to 1 plus half. So the number of terms in each term is different. So in this way, this sequence goes. And we are given that an is equal to this way. So an is given as the sequence, the nth term of the sequence is given as 1 plus half plus dot and finally plus 1 over n. So now we want to prove that this sequence given by this general term diverges. We want to prove that one. So what I'm going to do is I'm going to show that this sequence an does not, the sequence an is not bounded. I'm going to show that the sequence an is not bounded. Then by showing that sequence is not bounded, okay, I can say that it is not convergent. Do you understand this logic? This is what I am going to do. I'm going to show that the sequence an is not convergent. By showing that the sequence an is not bounded, I can directly say that it is not convergent from the contraposition of the previous theorem. Do you understand this logic, 77? Do you understand this logic? Do you understand what I am going to do? Okay, fine. So now I am going to prove that this sequence is not bounded. So in order to show that this sequence is not bounded, okay, normally we take the general term of the sequence, but here I am taking a particular term of the sequence. Particular term means that is also one of the general term. But I am taking a to n because I need some more terms. In order to apply some mathematical or inequality results. Okay, that is no problem. You can consider any term, and if you show that particular term is not bounded, because bounded mean what? An should be, what of an should be less than or equal to m for all n belongs to n, isn't it? So every term of the sequence should be bounded. So if one term is not bounded, then this entire sequence is not bounded. Therefore, for some mathematical trick, I'm considering the term a to n. Then a to n can be written in this way. Then what I am doing is I am now grouping this term. I'm grouping this term. How I am grouping this term? I'm writing the first as it is. I'm writing the second as it is. Then third term and fourth term together. Fifth term, sixth term, seventh term, eighth term together. And likewise, I'm writing. Okay, I'm writing like this. Why I'm writing? Because I'm going to use some mathematical fact. So here there are two terms. Here there are four terms. And there will be 8 terms in the next group, and it will go like that. The last one, okay, there will be n minus 1 terms. There will be n minus 1 term. Okay, the last one there will be n minus 1 term. Okay. Now, if you consider each of these terms, if you get the sum of each of this group, always greater than half. This part is always greater than half. And this part is always greater than half. Each of these subgroups, each of these subgroups every group subgroup will be greater than half, and there will be here n minus 1 subgroups. So n groups. So what you can write is, so each of these term is greater than half. So you have some terms. Say for an example, you have this term 1, 2, 3, 4. Okay, there are 4 terms. There are 4 terms, and 1 is here. This is 1. So this is greater than half. 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 Therefore, you can write the whole is the sum of this plus sum of this plus sum of this plus sum of this one is greater than 1 is great 1 plus how many things? 1, 2, 3, 4. So 4 divided by 2. You can write this greater than or equal. You can put that. Okay. Similarly, I am putting this one. This one is greater than half. This one is greater than half. This one is greater than half. Each of this one is greater than half, and there are n such thing. Therefore, I can write it as 1 plus. I can write it as, look at here, 1 plus the whole part is greater than. You can write the whole part is greater than or equal to this 1 plus there are n subgroups n into half. So that's how this 1 plus n by 2k. 1 plus n by 2k. Now you see that your one term in the sequence, that is the 2 to the power n term of 1 plus n by 2. Now what can you say about this one? What can you say about this one? This is not bounded because 1 plus n by 2 is not bounded. Why is that? 1 plus n by 2 is not bounded. Because when you put different n, it keeps going. Because if you draw this one, if you draw this one, actually what is happening? It is like this. No? It is like this. So it is growing without any boundary. It is growing without any boundary, isn't it? It is growing without any boundary. So this part is not bounded. This is not bounded, but even this one is not bounded. But this A2n is even greater than that one. Therefore, this is also not bounded. This is not bounded. Sorry. This is not bounded. So the smaller one is not bounded. Therefore, definitely right hand side is also not bounded. So if this is not bounded, then what you can say? It is not converged from the contraposition of the previous case. Do you understand now? 77, you understand now? Okay, thank you. Right, so let's move to the next hand. Right. So this is actually the last part of this one, last part of this chapter 2. That is about the monotonic sequence. So the definition is very simple. A sequence AN is said to be monotonically increasing sequence. Monotonically increasing sequence. That means that AN is less than or equal to AN plus 1 for all n greater than n. Similarly, a sequence is said to be monotonically decreasing sequence. That is, AN is greater than AN plus 1 for all n greater than n. So it is nothing. It says that a sequence, we are giving a new name for sequence, is monotonically increasing sequence. That means that if A1 is greater than or equal to, A2 is greater than or equal to, A3 is greater than or equal to. So if the terms of the sequence goes in this way, the terms of the sequence goes in this way, then such sequence we call it as the sorry, I have written other side. So I'm sorry. A1 is less than or equal to A2, less than or equal to A3. If it goes like this, then we say that such sequence as monotonically increasing sequence. It should happen for all n, not for some n. Okay, similarly, If it is other way around, like A1 is greater than or equal to A2, greater than or equal to A3, and if it goes like that, then we say that the sequence is monotonically decreasing sequence. Okay, so this is actually monotonically increasing sequence, and this one we call it as the monotonically decreasing sequence. Here, if strict inequality occurs in 1 and 2, that means that strict inequality means if you don't have equal sign, you don't have equal sign, then we say that that is strictly increasing sequence. And if you don't have here not equal part, then that we call it as the strictly decreasing sequence. So monotonically increasing sequence or decreasing sequence, also called increasing sequence. Without the name monotonic, sometimes we say that increasing sequence or decreasing sequence. So if you have the equal also, then we say that it is an increasing sequence. Then you can say monotonically increasing sequence, or you can say monotonically decreasing sequence. Okay. If you don't have equal sign, you can say monotonically strictly increasing or monotonically strictly decreasing, or simply you can say that strictly decreasing sequence or strictly increasing sequence. Okay, or you can simply say that strictly or increasing sequence or decreasing sequence. Okay, so just two definitions. Okay, just two definitions. Do you understand the definition? Do you understand the definition? Say for an example, if you consider the sequence 1 over n, then of course we know that first term is 1, the next term is half, next term is 1 over 3, and it goes. And obviously we know that this is less than, and like that, isn't it? Therefore, this is what? This is a decreasing sequence, monotonically decreasing sequence. So you can say that strictly, because nowhere we get equal sign. Therefore, you can say that strictly decreasing sequence. Say for an example, if you have a sequence like n, if your sequence is n, then you can write 1, 2, 3, like that is sequence goes, isn't it? Then obviously we know that this is greater than that one, this is greater than that one. Therefore, this is what? Sorry, I'm sorry. So this is less than this one, this is less than this one, it goes in this way. So this is increasing sequence. You can say monotonically increasing sequence, or monotonically, this one is monotonically decreasing sequence. This is decreasing sequence. So these are the examples. Do you understand this definition? Hello, do you understand this definition?
Yes, sir.
Right, fine. So now we have a theorem. Last theorem in this chapter, there are two parts in this theorem. One is, it says that every sequence which is monotonically increasing and bounded is converged. Okay. So when we talk about the sequence, we are always concerned about convergence. Okay, so we are always rounding around one important point called the convergence. Okay, convergence. In the previous handout, we looked at that bounded sequence may not be converged. Bounded sequence may not be converged. Okay, bounded sequence may not be converged. But if a bounded sequence with a monotonically increasing property, if a sequence is bounded plus monotonically increasing, then that is converged. Okay. Similarly, if a sequence is bounded below and monotonically decreasing, then that is converged. So try to understand this. Last time we said that bounded, the sequence bounded does not imply convergent. Does not imply the convergence. Isn't it? Does not imply the convergence. Now, what we are saying is monotonically, or you can simply say increasing sequence. It may be increasing or decreasing, no problem. Sorry, it may be strictly increasing or normally increasing. Increasing plus bounded above. Increasing plus bounded above implies as convergent. Look at it. Earlier one, bounded alone does not imply convergent. But if it is increasing plus bounded above, implies as convergent. Similarly, decreasing plus bounded below implies as convergent. Okay, so here is look at this one does not imply. So bounded alone does not imply convergence, but increasing plus bounded above implies convergence. Decreasing plus bounded below implies convergence. So that is what that is all about. This theorem talks about. That is all about this theorem talks about. Okay, every sequence. So now we are going to prove the first part, and from the first part we can easily prove the second part. Okay, so this is the proof. Look at the proof here. Suppose an, the sequence an is monotonically increasing sequence of real number which is bounded above. Okay, so now we are assuming the first part of that one. We are assuming that the given sequence is monotonically increasing and bounded. So that is our assumption. That is our assumption. Then we are defining a set as an, n belongs to n. So we are putting all the terms of this set into the set S. We are putting all the terms of the sequence into this set S. Then obviously what S is bounded above. Why S is bounded above? Why S is bounded above? Because now what we are doing is, okay, we have the sequence. Suppose we are saying that an is bounded above, and increasing sequence, monotonically increasing sequence. Monotonically increasing sequence. Now, so your an is like this. So a1, a2, like that. Now you are defining a set S. Now you are defining a set S. Capital S is equal to. You are putting all the terms of this sequence into this set A1, A2. You are putting all this. But since already it is bounded above, what is the meaning of bounded above? What is the meaning of bounded above? What is the meaning of this bounded above? Bounded above means an is less than m or less than or equal to m for all n belongs to n. Isn't it? Therefore, what can you say about this set? Therefore, you can say that the set S is bounded above. Okay. Bounded above. So now we are coming to the first chapter, bounded above. We have a set that is bounded above. So if a set is bounded above, then what can I say? Look at here. If a set is bounded above, hence by the least upper bound property, that means that completeness axiom. Can you remember that completeness axiom? It says that if a set has a supremum, least upper bound mean what? Least upper bound mean what? Least upper mean what? Supremum, no? Supremum. Supremum. So if a set has a supremum, then by the completeness axiom, we say that it has a supremum. So from the least upper bound property, that is the completeness axiom. But what does completeness axiom says? If a set is bounded above, then it has a supremum. That is the completeness axiom says. So if you remember the completeness axiom, it says that if S is bounded above, then S has supremum. So that is the completeness axiom says. So here we are saying that X has a least upper bound. So least upper bound is nothing but supremum. We are saying that that is equal to B. We are taking that as a B. Then we are taking that epsilon greater than 0. Then epsilon greater than 0. Then by definition of least upper bound, what you can write? There exists n belongs to n such that an is greater than b minus 3. So this is what? This is actually nothing but property S. Property S. Because there will be an element from this set. There will be an element from this set an such that an will be greater than b minus epsilon. Can you remember that? Can you remember that property? That we are trying to say that S is a non-empty subset, and if U is equal to supremum of S, if and only if there exists S epsilon. This is the second condition. There exists epsilon belongs to S such that for all epsilon greater than 0. Okay, so sorry, it should be the first one, no? So I'm sorry. So we are saying that for all epsilon greater than 0, there exists epsilon belongs to capital S such that U minus epsilon is less than S epsilon. Similarly, our set S has the elements an where n belongs to n. Therefore, we are saying that if B is the supremum, so we are taking B equal to supremum of S. Therefore, you can write it for all epsilon greater than 0. There exists n. Okay, there exists n belongs to set of natural number such that B minus epsilon will be less than that particular an. So that is what they have written here. That is what they have written here. An is greater than B minus epsilon. But we know that since an is greater than an for every n, because why we are saying an is greater than an for every n? Why we are saying? Because n is a monotonically increasing sequence. Therefore, if n is greater than n is greater than simple n is greater than capital N, then obviously we know that an is greater than capital N because a1, a2, here you are a capital N, and here an. Okay, then obviously what? It's monotonically increasing. So this will be graded. Then always you can write this way. AN is less than, okay, AN is less than AN. That is always less than B because this is the supremum. Then that is less than B plus epsilon. And this is less than B minus epsilon. Okay, that is B minus epsilon. Okay, very simple to understand. We are using, this is actually we are using the monotonically increasing condition. Then what we are saying here, look at here, AN is between, finally we are writing this, AN is between B minus epsilon and B plus epsilon. Therefore, what you can say, AN is from this one, you can write this one, AN is between B minus epsilon and B plus epsilon. Since epsilon is arbitrary, AN is between what? B and B. So AN is B and B mean what? Finally, AN tends to B as n tends to infinity. As n tends to infinity. So we are proving that AN converges. AN converges mean what? AN actually converges to supremum of that point. Okay, so that is what we are trying to prove here. That is what we are trying to prove here. Okay, that is what we are trying to prove. AN, because convergence mean what? Convergence mean what? AN minus, okay, AN minus B should be less than epsilon. Okay, B minus. So from this one, what you can write? So look at here. You are concluding that AN is less than B plus epsilon greater than B minus epsilon for all n greater than or equal to n. You have that one. So from this one you can write AN minus B is less than epsilon greater than minus epsilon for all n greater than or equal to n, isn't it? So this is what actually you can, from this one you can write mod of AN minus B less than epsilon for all n greater than n. So this is nothing but definition of limit, isn't it? This implies as limit AN n tends to infinity equal to B. Isn't it? This implies as limit AN tends to infinity equal to B. Therefore, we can say that AN converges to B as n tends to infinity. So that actually concludes that AN is convergent. So now we are saying that if a sequence is bounded above plus monotonically increasing, then definitely that sequence converges. Now to prove the second part, actually we are not doing much work here. To see the last part, okay, to prove the last part, suppose Bn is monotonically decreasing sequence which is bounded below. So now we want to prove that monotonically decreasing sequence which is bounded below is convergent. That is what now we want to prove the second part of this theorem. So instead of proving that, what we are going to do is we are defining a sequence AN by multiplying the sequence by minus. So now what can you say about that? Now we have the sequence Bn which is bounded below plus decrease. Now I am defining AN as minus Bn. I am defining AN as minus Bn. Now what can you see now? If I define AN as minus Bn, what can I say now? Now the sequence AN is bounded above, because already Bn is bounded below and decreasing now. Therefore, if I define my new sequence An as minus Bn, if I define my sequence An as minus Bn, then An is bounded above plus. Now earlier it was decreasing now, so minus means it is increasing. Increase. So already we have proved that. So in that case, it says that then it is seen that the sequence A defined by An equal minus Bn for all n is monotonically increasing and bounded above. Hence, by the first theorem, An tends to A for some A belongs to R. A belongs to R. Then Bn tends to B, which is equal to minus B. So the first one, what we said actually, we said that. Look at here. We said that from now it is from that earlier one we said that An tends to A, isn't it? An tends to A. An tends to A. Because An is bounded above. Now we are saying that An is equal to what? An is equal to what? Minus B. Therefore, this will tend to, sorry, I am sorry here. Yeah, A from the first theorem, An tends to A for some A belongs to R. A belongs to R. Okay, for A tends to A. For A tends to A for some A belongs to R. Yes, A for some A. So if A tends to A for some A belongs to R, then what will happen to Bn? Bn will tends to minus. Okay, Bn will tends to minus. Okay, so Bn will tend. Sorry, Bn will tends to. Sorry, I'm sorry. Bn will tends to. Bn will tends to B, which will be equal to minus B. Should be equal to minus. Because in the earlier one, if that means that if An tends to A, if An tends to A, then if you define a sequence An as minus of Bn, okay, minus of Bn, then if Bn tends to B, if Bn tends to B, then that will be equal to minus of B. So that is what we are trying to say here. That is what we are trying to say here. Okay. So actually we are using the second part of this second to prove the second part. We are not doing anything. We are actually defining. We are actually converting this decreasing partition into increasing partition. Sorry, increasing sequence and bounded below. Because if you multiply by minus, all the decreasing will become increasing, bounded below will become bounded above. Then using the first result, we try to say that that also will convert. That also will convert. So that is what that is end of it. Do you understand now? Do you understand, students? Hello,
Yes,
do
sir.
you understand?
Yes, sir.
Okay, fine. Then, okay. Then we have 3 more examples. I don't find time to discuss that. Okay, in the next class, I take half an hour to discuss this 3 questions, and then I will start functions in the next class. Last chapter functions in the next class. I want to have some additional classes because it seems that strike will continue till 27th or something. Still no any decision or given, no any solution given by government. So the non-academic people are planning to continue their strike until further notice. Therefore, hopefully next week also it will be strike, I think. So, do you have any lectures during Friday morning or something? Do you have any lectures during Friday morning? Around 8 to 9 to 11 something? Do you have any lectures? Shall we have a extra class on Friday? 2 hours, 2 hour extra class on Friday on real analysis. What about others? Do you have any classes on Friday morning? You give me some more times because last week also because during the previous strike and holiday I couldn't take many lectures. So I think this is our sixth class or something. The seventh class. I think. So do you have any lectures on Friday? Friday morning or evening? Do you have any lectures on Friday? Please tell me. Okay, if you don't have any lectures, I will put a. I am going to put a class from say 9 to 11 something on Friday. This 92. Do you have class? What class you have? 92. What class you have? 92. 92. What is the lecture you have Friday morning? Can you tell me what class you have? Ninety-two.